Hi there, it's Miss Barbara again. We are working with computing z-scores. For data that is approximately normally distributed, the z-score describes how many standard deviations a data item lies above or below the mean. To compute a z-score, we use the formula. Z-score is equal to the data item minus the mean, all divided by the standard deviation. Memorize this formula. Data items above the mean have positive z-scores. Data items below the mean have negative z-scores. The z-score for the mean is 0. Example: the age at which babies develop the ability to walk is approximately normally distributed with a mean age of 12.8 months and a standard deviation of 2.3 months. Find the z-score of a baby that walks at 10 months. Let's identify the formula that needs to be used here. We're looking for the z-score, so we need the z-score formula, which is z-score is equal to data item minus mean in the numerator divided by the standard deviation. Now let's identify the parts. The data item is 10 months, the mean is 12.8 months, and the standard deviation is 2.3 months. Fit those parts into the formula. So z-score is now equal to 10 for the data item minus 12.8 for the mean divided by 2.3 for the standard deviation. Arithmetic takes us to negative 2.8 divided by 2.3, and that quotient is approximately negative 1.22. This one is tricky. The mean age for developing the ability to walk is 12.8 months. We're looking for the z-score of a baby who developed the ability to walk at 10 months. That is, he did it earlier. In this instance, the lower, lesser, or smaller values are better, so we take the opposite of the sign and conclude that the baby's z-score is a positive 1.22. Example: ACT scores are normally distributed. The mean score of a student accepted at a state university is 23.5 with a standard deviation of 4.6. A prospective student has a z-score of negative 1.25. What is that student's score? Let's identify what we're looking for. We're looking for the data item given the z-score, so we'll still use the z-score formula, which is z-score is equal to, in the numerator, data item minus the mean, divided by, and in the denominator, standard deviation. Let's identify the parts. The problem tells us that the z-score is negative 1.25. The mean is 23.5, and the standard deviation is 4.6. Let's put those numbers in the right places in the formula. That will give us negative 1.25 is equal to the data item minus 23.5 divided by 4.6. We're going to algebraically solve for the data item value. To do so, let's multiply this above equation through by 4.6. That will give you an equation that is negative 1.25 times 4.6, and that's equal to the data item minus 23.5. Have your calculator out if that'll help. Multiply the negative 1.25 with the 4.6. The product is negative 5.75, and that is equal to the data item minus 23.5. Now just add 23.5 to both sides of the equation and you can solve for the data item. That is, the data item is equal to negative 5.75 plus 23.5, and that sum is 17.75. The student's ACT score is 17.75. Measures of position. Measures of position are often used to make comparisons. Two common measures of position are quartiles and percentiles. Let's think about percentiles. A percentile interpretation of z-scores provides the percentage of data items that are less than any one data item. So, if n% of items in a distribution are less than a particular data item, we say that the data item is in the nth percentile of the distribution. Continuing with measures of position, let's consider quartiles. What is presented for us here is a normal graph with 3 points marked along the horizontal. Notice that it is equally by area split into 4 parts, that's 25% each. The first quartile, as you can see, is marked. It is also the 25th percentile. The second quartile is where the mean is. It is also the 50th percentile, and it's also the median. And finally, the third quartile is to the right of the second quartile, and that is the 75th percentile. To find the quartiles of a data set, first, order the data from the smallest to largest. Next, find the median or second quartile of the data set. If there are an odd number of data items, the median is the middle value. If there are an even number of data items, the median is halfway between the two middle items. Next, find the first quartile. The first quartile is the median of the lower half of the data set. Find the third quartile, which is the median of the upper half of the data set. Example: the weekly grocery bills for 23 families is given below. Determine Q sub 1, Q sub 2, and Q sub 3. That is, find the first quartile value, the second quartile value, and the third quartile value. For this problem, we're going to use the TI-84. This is a TI-84 plus CE calculator. We'll use this tool to compute Q1, Q2, and Q3. We begin by entering the data, so hit Stat, and then the one which is with the word Edit pops up by default. Select Enter. Under the L1 column, enter all 23 grocery bill prices. We'll start with 170, 210, 270. Fast forward through the data entry. $172, $190. Take a moment to make sure you got all the numbers in correctly, and after you do that, get out of the screen that is Quit It. To do so, hit the blue second and the button right next to it which says Mode, and you get to quit the screen. Now we're going to compute what we're looking for. Select Stat again. This time scroll right to select Calc for Calculate. The default selection is the number 1, which is for one variable stats. Select Enter. Continue to hit Enter and Enter again, and then at the Calculate, hit Enter one more time. Now all our values are here. To find them though, you have to scroll down and you'll see Q1 is 95. Median, which is Q2, is 190, and Q3 is 270. Q1, or the first quartile, is 95. Q2, as displayed on your calculator, is the median, which is 190, and Q3 is 270. Example, the weight of infants is normally distributed. A 6-month-old infant is in the 75th percentile of weight for babies her age. What does that mean? The 75th percentile means she weighs more than 75% of babies in her age category. Let's consider margin of error. The definition: if n is the sample size, there is a 95% probability that it lies within 1 divided by the square root of n of the true population statistic. The formula plus or minus 1 divided by the square root of n times 100% is called the margin of error. Example, in a random sample of 1,172 children ages 6 through 14, 17% of the children said getting bossed around is a bad thing about being a kid. Part A, compute the margin of error. So identify the formula here, and that would be plus or minus 1 divided by the square root of n times 100%. Now let's identify the parts. The n is the sample size, and the sample size is n equals 1,172. Complete that formula, and you will get plus or minus 1 divided by the square root of 1,172, and multiply that by 100%. That value is approximately 2.9%. Part B, find the confidence interval. The definition of the confidence interval is the sample mean plus the margin of error, comma, the sample mean minus the margin of error. So let's compute this. In the statement of the problem, we learned that the mean is 17%, and the margin of error, we just computed it as 2.9%. Putting in the numbers, 17% minus 2.9%, comma, 17% plus 2.9%. Perform the arithmetic and you get the confidence interval is 14.1% to 19.9%. C. Write a statement about the reliability of the percentage of children who feel that getting bossed around is a bad thing about being a kid. An appropriate statement might be, there is a 95% probability that the true population percentage of children who feel that getting bossed around is a bad thing about being a kid is between 14.1% and 19.9%.